This is problem number 11 for the sample test problems for test number 3. Radioactive cesium-137 has contaminated the groundwater at a nuclear waste storage site in Hanford, Washington. Cesium-137 has a half-life of 30 years. The 137 is irrelevant to us. I'm sure it has meaning to a chemist. Part A, what percentage of the cesium-137 presently contaminating the site will be present in 100 years? So the formula that we need is the formula for half-life, and that formula is this one. M of T represents how much stuff, how much cesium in this case, is left after T years. And M0 is the initial amount of cesium, and then 1/2 is half-life part, and then T is the number of years that we're waiting. H is the half-life. So let's see if we can plug everything into that formula. So the amount of stuff left after some number of years is M0. I don't know how much stuff is in there in the beginning, so we're just going to call it M0 times 1/2 to the T. Let's see, I guess we're waiting 100 years divided by H. H is the half-life, which is 30 years. So that's the formula that tells you how much stuff you have in there at the end of 100 years. I want to know what percentage will be present 100 years into this experiment. So let's just go ahead and type in this thing into the calculator. Again, I don't know what M0 is, but I can type in this part. So we're typing in 100, typing in 1/2 to the 100 over 30. Again, make sure you're careful. You need parentheses up there in the exponent. So 0.0992. So this is roughly 0.0992 times M0. So whatever amount of stuff you had in the beginning, M0, you have 0.0992 of it left at the end. And I think that right there is our answer. 0.0992, which is 9.92%. That's how much stuff will be there 100 years into this experiment. Part B, the groundwater is predicted to be safe again when only 0.1% of the present cesium-137 remains. How long will this take? You will need to use a calculator to answer this question unless you already know logs. Before we get to the calculator, let's write the equation we're trying to solve. We're looking to get down to 0.1%. So apparently we're going to have to wait more than 100 years because after 100 years, we were still at almost 10%. So what we're trying to do is this equation. We know that the formula is M0 times 1/2 to the, now it's a T. I don't know how long I'm supposed to wait, but 30 years is always the half-life for cesium-137. And we're trying to get to 0.1% of the amount present initially. So the amount present is M0. And I want to know when we get to 0.1% of that. Well, 0.1 as a decimal is 0.001. So 0.001 M0, that's 0.1% of what we start with. So that's what we're after. We need to solve that equation. Okay, to solve this equation, well, we're going to use the calculator, but we can't use the calculator yet because there's an M0 and a T. But if you divide both sides by M0, then you see that the M0's canceled. So the equation we're really trying to solve is 0.001 equals 1/2 to the T over 30. And in a previous problem, we had an equation like this where the variable was in the power. And you need something called logarithms to solve an equation like this. We don't have them officially yet, although if you already know them, feel free to practice. So we're going to go to the graphing calculator. Okay, so we'll clear this stuff, and we're going to graph both sides of this equation, 0.001, and then up above, 1/2 to the, and then don't forget the parentheses. We need T over 30. I don't have T, I have X. X divided by 30. Okay, I guess I could hit graph. I'm on a window from some previous problem. No surprise, I don't see anything at all. So let's go into the window. I guess you could do the standard window and see what you see. Zoom and then 6 is the standard window. Okay, I see something there. I don't know how helpful that's going to be, and I don't see the second thing. Remember, I was expecting to see two different things, and I didn't see this one at all, the 0.001. It's supposed to be a horizontal line. Again, really just spend the time thinking about a good window. Save yourself the frustration of zooming in and kind of randomly looking around, hoping that you can find the intersection. X in this problem stands for time. The question is, how long is it going to take? Well, according to the previous problem, if you wait 100 years, you still had 10% of the stuff left. And we're trying to get a lot less than 10%. So we're going to have to wait a lot more than 100 years. So the X that we're interested in, let's see, so we can start this experiment at 0 years, but the answer here is definitely more than 100. I'm willing to try 1,000 and just see where it goes. Again, we can play with that. We're just making our best guess. And then the Y values in this case are the percentage of stuff left. And we're interested in knowing when the percentage is down here at 0.001. That's a really small number, and that's the only number I need to make sure I can see. So let's see, percentages don't get less than 0. Even if you put 1, you're not going to see it, I don't think. So we want to put something really, really small. I'm going to like triple that number, 0.003. But definitely I'll see 0.001 in here. So we hit graph and hope for the best. There's your exponential decay, and there's 0.001. And again, I think it's really, really valuable to spend time thinking about the window. It would take an awful long time to find a good window for this guy. This is really, really tough to find randomly. So you kind of have to think about what you're looking for. From here on out, it's easy. Really finding that window is the tough part. Okay, so we'll do second calc and then intersect. First curve, enter. Second curve, enter. Guess, enter. We'll see two numbers. The x value is t, it's time. So it takes about 300 years. And the y value is that amount of stuff that's left. So 0.001 of the starting stuff will be left after about 300 years. So we'll get a screenshot and then we'll put our answer. Okay, so we've got our screenshots of the equation, the window, and then the graph. And so putting them all together, we find that after about 298.97 years, we will be down to 0.1% of the present cesium-137, at which point it's safe to go back in the water.